Howdy everyone, and welcome to the Chapter 17 example problem video. Here we'll be looking at a few equations dealing with titrations, a little bit of Henderson-Hasselbalch maybe, and some solubility products. Alright, so let's go ahead and get started. The first one, we're preparing a hydrofluoric acid and fluoride buffer, and it's asking us what is the pH of a 1 molar solution of hydrofluoric acid, so kind of where would it start? And then how many grams of sodium fluoride should be added to make it this pH 3 buffer. Well, this first part, when you're finding out the pH before you start, that's just the normal problem from chapter 16 of, hey, we have this molarity of an acid, what's the actual concentration, what's the pH going to be? So we look up the Ka like we did, so I got that here, hydrofluoric acid is, oh, that's not what I want. The Ka is 6.8 times 10 to the negative fourth. So we just plug that in. Okay, 6.8 times 10 to the negative fourth is equal to x squared over our initial concentration, so 1 molar. That means when we plug that into our calculators, 6.8 times 10 to the negative fourth, we'll just square root that because it was times 1. X equals 0.026 molar, and yeah, that would make this like 0.98. That's within the 5% acceptable for the assumption of not having to do minus x there. So that would be molar, and so if we take the negative log of that, we would get that the pH is equal to 1.58. So pretty acidic, but you can see, okay, we need to get the pH up to 3.0. That means we're going to use the Henderson-Hasselbalch equation that says the pH will be equal to the pKa plus the log of A minus over HA, concentrations for both. Now the nice part is, oh, we have the HA, we have 1.00, and so it's like, okay, great. Well, because we're just adding in a solid, the problem even says assume any volume changes are negligible. So while these are concentrations, what we really care about is just moles over moles. So we can say, okay, if it's a 1 molar solution, and in the problem it did say that it was a 1.25 liter solution total, we just need to say, okay, how many moles then do I need to get this right? So first we got to solve for this fraction. So we want 3.00 to equal the pKa, so take the negative log there of 6.8 times 10 to the negative fourth. That's not what I want. 6.8 times 10 to the negative fourth. Take the log. Okay, so that equals 3.17 plus the log of our A minus over 1.00. So we can just plug all that in. We can then solve and say, okay, that means the log of A minus over 1, so just basically the log of A minus, is equal to negative 0.17. So that means we take the 0.17, negative 0.17, 10 to the x on both sides. That means the concentration of A minus must equal 0.68 molar. Okay, so if we get that, we say, okay, and that makes sense. If we have more base, the pH will go up from this 1.58. Yep, that makes sense. But we do want the pH to be lower than the pKa, so it makes sense for there to be less conjugate base than there is acid. So everything is looking good so far. Well, now we just got to say, oh, if I need 0.68 molar in a 1.25 liter solution, we just say, okay, 0.68 moles per liter times 1.25 liters. That's going to be 1.25, 0.85 moles. And then we just say, okay, 0.85 moles times the HF. Oh, no, sorry, no, this is sodium fluoride, not the HF. See, 22.99 plus 19 should be 41.99, yeah. All right, so 41.99 grams there, times the 0.85 moles. That means we need 35.7, I guess the two figures would be 36 grams of sodium fluoride. And let's go ahead and take a peek at our answers for chapter 17. Haven't looked at these, just to make sure they didn't want anything weird on this one. 25. A, pH of 1.58, and B, 36 grams. Yep, so we did everything right there. So that's how you do that one. So if you're ever tasked with finding out how much you need, that's how you can use the Henderson-Hasselbalch equation to say, okay, I know the pH I want, I know the pKa from my Ka, I'm figuring out this fraction, right? So you just kind of simplify and then solve for it. You get it? And then don't forget, if they give you liters and it's not 1 liter, you gotta say, oh wait, my molarity, I gotta adjust to see how many moles I actually need to get to grams. All right, next problem, 1747. It says the problem is to calculate the pH at the equivalence point if you're titrating each of these 3 bases with the strong base hydrobromic acid. In your homework, I've given you a problem where it's titrating 3 acids with a strong base, so it's going to be a very similar problem, just kind of reverse it. In the case of A, this one's the simple one. We have a strong acid, hydrobromic, we have a strong base, sodium hydroxide, so by definition, at the equivalence point, the pH is going to equal 7. You don't have to do any math with that one. When it's strong with strong, it's always at pH 7. Now here for B, the trick is going to be that if we have 0.2 molar NaOH, and I should say in the book, this was also titrating with 0.200 molar HBr, that we're going to say, okay, we're going to have to find out what will the concentration of the conjugate be, because at the equivalence point, all of this base has been reacted, but it's all been converted into the conjugate acid. So we're going to have to say, well, what's my concentration of the conjugate acid? And then from there, what would the equilibrium be using the Ka equals Kw over Kb? So this problem is going to be a little bit more involved, but you're going to do a similar thing with the acids. All right, so that means at the equivalence point, now this one, it's a little simple. If it's 0.2 molar acid and 0.2 molar base, that means it will be equal volumes. So at the equivalence point, the total volume is going to be double. So that means at the equivalence point, we're going to have 0.100 molar NH2, well, NH3 OH plus. That's how it would be written there for the this hydroxylamine, and then, yeah, it would be hydroxylammonium. So we got to look that up. So I'm looking in Appendix D for the bases. The Kb for this hydroxylamine is 1.1 times 10 to the negative 8th, which means that, okay, we say that Kw equals Ka times Kb, so the Ka is going to be Kw divided Kb. So the Ka for this species is going to be 1 times 10 to the negative 14th divided by, in this case, 1.1 times 10 to the negative 8th. Let me try that again with my calculator. 1.1 times 10 to the negative 8th. And so we get 9. Well, it's 090909. So it's 9.1 times 10 to the negative 7th. And then we just do our normal calculation. We'd say, okay, that's going to be equal to x squared over the initial concentration, which is 0.1 molar at this point. That means x is going to equal, let's see, 9.1 times 10 to the negative 7th times 0.1 square root. X is 3.0 times 10 to the negative 4th. Take the negative log of that. The pH is going to equal 3.52. And we'll just check the answer real quick again to make sure that that is what they wanted me to do with the volume. I suspect that was a trick they were looking for. This is 47. Yes, the concentration is 1 molar So the pH is 3.52. So that's the trick. I believe on the homework problem I gave, it's like 0.1 molar acid titrating 0.08 molar base. So it's not going to be double the volume and exactly half. You're going to have to say, well, wait a minute, what volume would I need? What's the volume ratio? And apply that to get your molarity. I've also dropped my pen. Clearly the most professional video I've ever made. All right, same thing is going to happen here. This is aniline, it looks like. So at the equivalence point, with this one, again, it's going to be 0.1 molar because it's going to be equal volume, so that each molarity drops in half. And it's going to be C6H5NH3 plus. If we look in the appendix here, aniline is 4.3 times 10 to the negative 10th for its Kb. So then if we apply that, same equation that we did before, so the Kw divided by the Kb. In this case, the Ka for the protonated aniline is 2.3 times 10 to the negative 5th. Again, we'll say that's x squared over 0.1 molar, which means that x is going to be equal to 1.5, it's like 1.524 times 10 to the negative third. So yep, that's still small enough to be a good assumption. And if we take the negative of log of that, and I always recommend don't round it, like you can write down that 1.5, but keep it in your calculator, don't round it if you don't have to. That pH will be 2.82. 2.82, and that is correct with the answer key. All right, so that's how you do that one. Just it was a little bit easier in this one because it was equal volume. But yeah, use the ratio of what would it be between a 0.1 molar base and a 0.08 molar acid, or whichever way it goes. What will the final volume have to be compared to where you started, just on a ratio standpoint, and that tells you what to do with your molarity. In this case, I had to double the volume, so the molarity was in half. All right, the last problem here is doing molar solubility of silver bromide. I'm only doing the A and C here, so in pure water, so no ions present. And then in C, with a 0.1 molar sodium bromide, so that's going to be with the common ion effect. If we've got bromide already, what does that do to our molar solubility? All right, so we have to look up silver bromide here in the book. There it is, AGBR. This KSP is 5.0 times 10 to the negative 13th. And so we just say, okay, for in pure water, the KSP, well, for both of them, is going to be the silver concentration times the bromide concentration. So in this case, 5.0 times 10 to the negative 13th will equal x times x. So x squared. So in this case then, x, which is the molar solubility, that's my molarity, is just going to be the square root of that. So it's 7.1 times 10 to the negative 7th molar. That's the answer, nice and simple. But now for C, this is where we get into common ion effect. It'll still be the same one, but now it'll be, okay, 5.0 times 10 to the negative 13th. The silver concentration is still going to be x, but because I'm starting with 0.1 molar bromide, that means the bromide concentration is going to be 0.10 plus x. So, okay, we can multiply this through, get a quadratic and solve, or we can say, well, wait a minute. In this last problem, x was 10 to the minus 7. Whenever we have common ion, less dissolves than normal for an insoluble thing. So x, in this case, should be smaller than 10 to the minus 7. If it's smaller than 10 to the minus 7, it's never going to affect this 0.10. So I can simplify this and say, oh, it's going to be x times 0.10. And then when I solve for x, I'll plug it back in, make sure that's reasonable, but it will be. So in this case, we just take 5.0 times 10 to the negative 13th. We're going to divide by 0.10, and that means x is equal to 5.0 times 10 to the negative 12th molar. So it's going to be a much smaller amount that dissolves because we've already got some bromide present. And if we check this as 57, yeah, first one 7.1 times 10 to the minus 7th molar. Letter C, 5.0 times 10 to the minus 12th molar. So that is correct. All right, so hopefully these were helpful to you for chapter 17. Like I said, the trickiest part is sometimes, like in part 20, or problem 25 here, when we're doing Henderson-Hasselbalch, here the total volume didn't matter to find the molarity, but the volume did matter to find out moles and grams. So sometimes the volume matters, sometimes it doesn't. Here in 47, you had to say, wait a minute, if I titrate, if I'm adding a solution, I'm changing the volume as I go, so the molarity is changing as I go, irrespective of the things reacting, and so the pH is also changing for that. So you always got to watch out. Am I changing the volume? And if I am, is that going to change my number somehow? So please watch out for that as you're doing these problems. All right, that's going to do it for chapter 17. Have a good day, everybody. See you soon.